Hello there guys, welcome back to another epic and extra maths video. We're doing a bit more Laplace transforms. So in this video, we want to find the Laplace transform of t to the n. So I've also written something up here as well. Now this may seem alien, it may seem familiar. This function here, which looks kind of crazy in and of itself, is called the gamma function because this letter here that kind of looks like an R is actually a capital gamma, and that's a Greek letter, of course, gamma. So what is it? It's given by the integral from 0 to infinity of some dummy variable x to the z minus 1 multiplied by e to the minus x dx. And it turns out that if we say that this is some function of z here, it turns out that, depending on what value for z that you choose, it's actually equal to z minus 1 factorial. So for example, let me just give you a quick example. You might, because this is related. So for example, if I was to find the gamma function of, let's say 4, something like that, then this would be the integral from 0 to infinity of x to the 4 minus 1, so 3, e to the minus x dx. And this, strangely, is equal to 3 factorial. So it's whatever number is in the power, it's equal to that number factorial. So if you had a z, it gives you just one less than the number that you put in factorial out. I'm not going to explain why this is the case. I'm sure I'll do a video on it in the future. If I do end up doing a video in the future, the link will be in the description to this one. So just check the description. If the link's there, I made the video. But it's an interesting result. It's called the gamma function. It's an interesting situation. Something that's quite interesting about it, actually, is, as you can probably imagine, factorials. And again, just to note, so there's no ambiguity, 3 factorial means 3 times 2 times 1. So you're multiplying every whole number until you get to 1. So you start from the number that you're taking the factorial of, like 3, and you just multiply by every integer until you get down to 1. That's what factorial means, if you didn't know. Now, so it's quite strange. So this integral would be equal to 6, for example. It's quite strange, right? But as I was saying, what it lets you do is find the factorial of numbers that are not natural. Because of course, if I said to you what's, I don't know, a half factorial, or something like that, or pi factorial, you would say that doesn't make any sense. How am I supposed to work that out? But this integral lets you work it out, because there's nothing here that stops you, per se, from being able to choose numbers that are not natural. One thing that does not work here is you cannot choose negative integers. Negative integers do not work. You cannot find the factorial or the gamma function of negative integers. Okay, so this is just an aside because it's related to our function here, you'll see. So we want the Laplace transform, back to that, of t to the n. So you could think of n as being a natural number, so we want the Laplace transform of t, or t squared, or t cubed, or t to the 105, something like that. But you'll find, because we're about to employ this gamma function here, you will find that actually you can find t to any power except negative integers. So you can't find the Laplace transform of t to the minus 1 like this, or t to the minus 3 or something like that. But you can find the Laplace transform of the square root of t, or the cube root of t squared, or something like that. Any one you want. And I don't see why you couldn't also find something like the Laplace transform of t to the power of root 2 or something like that. I've never tried that. I don't know how difficult it would be. Maybe we'll do a video on that in the future, but I don't see why you couldn't. I'll do a little annotation on the screen right now, let you know if you can or cannot do that, because I actually don't know off the top of my head. Okay, so let's just go straight in. There's been enough talking, let's go straight in. I just wanted to explain this because we're about to use this, and I don't want to scare anyone away. Okay, Laplace transform t to the n. This is equal to the integral from 0 to infinity of t to the n times e to the minus st dt. Now you might already see a similarity between what we've got here and what we've got up here. I'm just using different letters of the alphabet, but you've got something to the power of a number times e to the power of a negative thing with respect to t, where it's the first thing is being raised to the power of number, that's the base with respect to the base. So t dt, right? X dx. The power is also an x up here, it's negative. And also the power is the variable there as well. It's a t, it's negative. You can see the similarities, but they're not the same. They're not the same because you have this minus s. So what we want to do is we want to do a substitution to make it resemble the gamma function. So what we're going to do here is we're going to because what we would really like is for this st to basically just be like a t or a variable. So I'm going to say let u equal st. This will be our substitution here. So it's a u substitution. Okay, that means that du dt would be s, because s is a constant, so it's just differentiating a constant times t. That means that du is s dt, meaning that dt is just 1 over s du. Okay, lovely, 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 lovely. Now let's go back into our integral. So it's the integral. Let's also change the limits up here. So if t is 0, then u is just s times 0, so that doesn't change. And also, not in a formal way, but just, just work with me. If t was infinity, then u would be a constant times infinity, so still infinity. I know that's not a very formal way to do it, but the limits do not change. Okay, now t, we don't want t anymore, so t can be written as u divided by s, can't it? So this is u divided by s to the power of n times e to the minus, and then st, of course, is u. So u, and then the du, dt, sorry, becomes 1 over s. So I'm going to put the 1 over s out the front, du. Okay, this is our integral here. Lovely. Okay, so I'm going to keep the 1 over s on the outside. I'm going to simplify the inside a little bit. So this is the integral from 0 to infinity. This becomes u to the n over s to the n, e to the minus u du. And this becomes 1 over s, and I'm actually going to factor out a 1 over s to the n because it's a constant. S is a constant, n is a constant. So if I take out 1 over s to the n, I end up with 1 over s to the n plus 1 on the outside because there was already another 1 over s there. Then we have the integral from 0 to infinity of just u to the n, e to the minus u du. Now this is the gamma function. Technically, the n would need to be like an n minus 1 or something like that. But you can see here, we could just consider the number that's in the power is what you take the factorial of. So if there's a 3 in the power, it's 3 factorial. If there's an n in the power, it will be n factorial. Notice though that this really is completely identical to this very top line. It's just that the x's are u's and the z's are actually n's here. That's the only difference. Everything else is the exact same. It's offset kind of by a minus. So instead of z minus 1, it's just n. But that's completely fine. It's just a constant. So we can just consider, again, that if z minus 1 was just a number like n, then it would be n factorial, right? So it's the same thing. So this integral, and again, we're not going to prove it in this video, but this integral is n factorial if n is a natural number. If n is not a natural number, then you just leave it as the gamma function, and technically it's the gamma function of n plus 1, because the gamma function of n has got a minus 1 there. So don't worry about the thing, don't worry about it too much. But let's consider two cases. If n is a natural number, put that there. If n is a natural number, then the Laplace transform of t to the n is just given by 1 over s to the n plus 1 times this, which again, this is n factorial. So it's n factorial divided by s to the n plus 1. Okay. So if you wanted to know, for example, I'll do an example at the end. If n is just any other real number, but not a negative integer. So not, we'll say z negative. So not a negative integer. Okay, not negative. It can't be a negative integer. If that's the case, then we just consider that the Laplace transform of t to the n is, and we write it as the gamma function of n plus 1 over s to the n plus 1. Okay. So for example, if you wanted, let's do some examples here. Let's start with the case where it's a natural number. Let's say we wanted the example. Let's say we wanted the Laplace transform of t. Let's go with t cubed. T cubed. Okay, the Laplace transform of t cubed. Well, we just look at the formula, and it's just 3 factorial because that's n divided by s to the power of 1 more than that. So s to the power of 4. So that would be 6 over s to the 4. That's our Laplace transform of t cubed. Lovely. And if we wanted the Laplace transform of, let's go with t to the power of, why not, let's go with a half. T to the power of a half, so the square root of t. This would be equal to the gamma function of 3 over 2. So just, again, it's 1 more than that, divided by s to the power of 1 more than a half, so to the 3 over 2. And I'm going to look up right now what the gamma function of 3 over 2 is because I don't know. I've got an answer. The gamma function of 3 over 2 is the square root of pi over 2. So our Laplace transform of t to the power of 1/2, which I could also write as just the square root of t, strangely is the square root of pi divided by 2 times s to the 3 over 2, like that. So yeah, it's quite weird that pi pops up there, let alone the square root of it, but that would be our Laplace transform there, guys. So this was a weird one. We actually did quite a lot of, I would say, pretty complicated stuff, actually, to be honest with you guys. Hope that was helpful. It looks like quite an easy one, doesn't it? Just, oh, okay, what's the Laplace transform of t squared? I wonder what it is. Well, actually, it's a big mess. But I hope that was helpful nonetheless, guys. Pretty exciting stuff, and I'll see you in the next video. Cheers.